In this next module, we're going to talk about probability distributions. I'll also call these probability functions. So first of all, a probability function or a probability distribution, it just gives the probabilities of all possible outcomes. So last week, we calculated the probability of a particular outcome. If you calculate the probability of all possible outcomes, or if somebody gives you those to you, then you have a probability distribution. You can think of it as a mathematical function that takes the possible outcomes x and maps them to a probability p of x. So we could think of this as a mathematical function. That's helpful in some cases. The probabilities, when you have the full distribution, they have to add up to 1. Otherwise, if you have mutually exclusive, exhaustive outcomes, their probabilities have to add up to 1. So that's the thing. One thing you can check that you've calculated probabilities correctly, though if you've calculated all of them, they have to sum up to 1. Now I am going to be talking a little bit about continuous probability functions, continuous mathematical functions in this week. When you're talking about continuous probability functions, summing up or adding up to 1 actually means integrating. That is involving a little bit of calculus. So I don't want to scare you, but if you want to see a little bit of calculus, I will be providing that this week. If you have never had calculus before, or integrals are just going to really throw you for a loop, don't worry about it. All we're talking about here is if we have some kind of mathematical function. So here's just a continuous mathematical function. When I say integrate, all I mean is that you're figuring out the exact value for an area under a curve. So if you could do that just by kind of measuring this area under the curve, you wouldn't need integrals. But what the integrals do for us is they calculate precisely what is this area under the curve. So that's all an integral does. If you don't want to see the integrals, they're optional. You can just kind of ignore them. But every time you see integral, just think of area under the curve. For those of you who have a background in calculus and are a little bit more interested in seeing a little bit of calculus tied in here, the reason I'm going to throw up these integrals here is just so you can see precisely how things are calculated, and also to give you a little bit of an appreciation for what calculus is useful for. So I didn't really appreciate calculus until I took statistics. Once I saw how calculus was so useful in statistics, it gave me this newfound appreciation for calculus. And my mother is a retired calculus professor, so I grew up with calculus all around me, and I really didn't appreciate it until I saw how it was applied to statistics. So that's why I'm going to throw in just a little bit of calculus here. Again, if integrals scare you, just think area under the curve. Probability functions can be discrete or continuous, and this is the same distinction we talked about in the first week of the course. So discrete means you can only take on certain values. So these would be things like whole numbers, counts. You're either dead or alive, treatment or placebo. You throw a die, it can only be, the outcomes can be 1, 2, 3, 4, 5, and 6. So it can only have discrete values. That's, of course, as opposed to continuous. Continuous variables can take on any value within a given range. So say any number between 1 and 6. It can take on 1.2, 1.235. So these would be things like blood pressure, the instantaneous speed of a car. So continuous things have an infinite number of possible values. For the most part this week, I'm going to focus on a lot of discrete examples because they're easier to deal with. They're easier to get your head around. We can then understand it using the discrete examples, and we can then kind of generalize, extend it to the continuous case. Whenever I'm talking about the continuous case, I'll be throwing in that little bit of calculus, a little bit of integrals this week. But I'll try to focus mostly on the discrete case because it's easier to grasp. So let's just take a simple example. Here's a discrete probability function. When you roll a die, there are 6 possible outcomes. So I'm just putting those on the x-axis. They each correspond, each of those outcomes corresponds to a certain probability that happens to be the same for all of them, just 1/6 probability. So we can draw that out in a graphic. The y variable here is the probability. So that's a very simple probability distribution. Notice that those probabilities add up to 1. Right? One of those things has to happen, so they sum up to 1. So all your probability distributions have to add up to 1. We can write those same probabilities in a table. So this week sometimes I'll be giving you a table that looks like this. So you have x, those are the possible outcomes. P of x, those are the probabilities that correspond to each of the possible outcomes. Another name we call this table a probability mass function. It just shows you how each of the outcomes maps to a probability. We call it a probability mass function because each outcome has a probability mass associated with it. Notice that they all add up to 1. So sometimes we talk about the probability mass function, that is the probability of any particular value. Sometimes we actually are more interested in the probability of a range of values. And when we're talking about the probability of a range of values, we call that a cumulative distribution function. And by convention, cumulative functions always start with the lowest value and go to the highest. So here's that same example of rolling a die presented as a cumulative distribution function. So now we're not talking about the probability of getting exactly 1, but the probability of getting 1 or less, which is 1/6. The probability of getting 2 or less is 2/6. The probability of getting 3 or less is 3/6. And then all the way up to the probability of getting 6 or less is 100%, because when you roll the die, you have to get 6 or less. So again, this is just a way to describe the probability of ranges of values. And by convention, we always talk about the probability of getting something or less than that. The probability is to the left. So let me just write that same cumulative distribution function out in a table. It's nothing profound here. Again, we're just showing this is the probability of getting 1 or less, 2 or less, 3 or less, etc. We call that a cumulative distribution function. This is especially important when you get to the continuous case, because you're always talking about ranges of values when you're doing a continuous function. Here's another example of a simple probability distribution. So last week I showed you this information on blood types. And this is really a probability distribution. It's just presented in whole numbers out of 100, but you can get out of this the frequency, the probability of each of these different blood types. There's actually 2 variables here. There's RH status as well as blood type. So we can make this even simpler by collapsing it down to just the probability distribution for blood type. So 45% of people have O blood type, 40% have A, 11% have B, 4% have AB. Notice that those add up to 100%. You have to be in one of those categories of blood type. So that's yet another discrete probability function. Let's see how we can actually use these probability functions. So here's a little practice problem. Suppose that in a particular hospital, in the emergency room of that hospital, the number of patients seen in any given hour is represented here by X. And X can vary. In 1 hour it might be 9 patients, in another hour it might be 10 patients. And let's suppose that somebody has observed this emergency room for a while and they've figured out the probability distribution for X. And this is obviously an artificial example, because we're saying that there's always between 9 and 13 patients coming into this emergency room. I'm making it a simplified example. So imagine that somehow it's always that strict. But somebody's observed and they've figured out that 30% of the time it's 9 patients, 30% of the time it's 10 patients, 20% of the time it's 11, 10% 12, and 10% 13. And that's all the possible outcomes. Notice that those sum up to 1. If we've listed out all the outcomes, then the probabilities have to sum up to 1. So now we can answer just some simple questions based on this probability distribution. And notice that this is a lot easier than what we did last week, right, where I made you calculate those probabilities. Now I'm just giving them to you, and it's pretty easy to pick the probabilities up off the chart. So for example, if I say, what's the probability that in a given hour exactly 13 patients arrive, you just look in the table, well, it's 10%. You just grab that right out of the table. What's the probability that at least 12 patients arrive? So now we're talking about a range of values. So that's the probability that either 12 or 13 arrive. So we would just add those 2 up. So the probability that at least 12 patients arrive is 20%. What's the probability that at most 11 patients arrive? Well, at most 11 would mean 9 or 10 or 11. So I add up those probabilities, and that turns out to be 80%. There's an 80% chance that at most 11 patients arrive. And this would be a really useful piece of information for people in an emergency room. If you were the head of the emergency room, you need to know about how many patients you're expecting to come in any given hour in order to staff the emergency room correctly. So this has practical applications. Some of the important discrete distributions that you'll encounter in medical research are the binomial distributions. So these are distributions that are used in many, many cases. They're very general. The one I just showed you was a very specific case. The binomial is something that generalizes to any time where you have a binary outcome, a yes-no outcome. So whenever you have data that's dead or alive, treated or untreated, smoker or non-smoker, that follows a binomial. So that binomial distribution, which we're going to talk about in a module this week, underlies a lot of the important statistics in medical research. Another important discrete distribution that comes up in medical research is the Poisson distribution. And this is a distribution when you have things that are counts. So like how many cases of disease are occurring in a given area. Those are counts. Counts follow a Poisson distribution.